I will briefly introduce Matz. So he did his PhD at the University of Oxford in the group of Professor Philip Kukura in the field of ultrafast spectroscopy. And after his PhD, he went for postdoc in the group of Professor Nick Van Hulst at ICFO Barcelona, where he was doing postdoc under Marie Curie Fellowship. And he is currently Jean Meneko Young Investigator, also hosted by Professor Van Hulst. His research interest in the field of nanophotonics and holographic imaging. And yeah, I think he recently published several high-impact scientific articles on this field. So today's we will talk about high-speed 3D phototransient imaging over large volumes of view. So Matz, now you.
Thank you very much. Let me just double check. You can hear me?
Yes, we can hear you.
Okay, very good. Okay, so yeah, thank you very much for the introduction. Yeah, as already said, I'm going to try to introduce you a little bit to the things we have been doing over the, I don't know, the last few years. And we've basically been working towards kind of implementing 3D phototransient or photothermal, if you like, imaging over like 3D, large 3D volumes. Before I start, I just wanted to say I think this webinar has been fantastic so far. So thank you very much for organizing it. And just to summarize a little bit, I think we've had some great introductions in the first week, followed by something which I would call kind of visualizing heat by Bafu and Jixing Sheng. And then in the last session, we went more towards applications. And as you can see by the website, there's a lot more to come. I'm not going to give a lot of introductions because I thought, I mean, you or the chairman or Michelle published a really nice recent review on photothermal microscopy. Similarly, we have seen a very nice review on mid-infrared photothermal imaging, but I think given how the webinar is going, the best possible literature review is probably just to keep on watching the webinar. So with that said, let me just dive in. So I said I will not give a long introduction, just a very brief kind of recap on photothermal imaging. And the idea is kind of simple. So imagine you have a system, let's say you have a cell here, and there's some particles that we're interested in, let's say viruses. You can label them with some sort of label, be it dye molecules or gold nanoparticles, like in this case here. And then all you do is you deposit heat into these particles, and then you kind of detect this heat-induced change or photo-induced heating. Yeah? And there can be many different mechanisms that you use. You can change, for example, a refractive index change because of this temperature change. You can look at scattering cross-section changes. You could also look at volume expansion due to this temperature change. What we want to do is kind of take this kind of simple 2D cartoon picture here and transfer it into let's call it a 3D box. So similar to this, imagine now with different kind of particles. Some of these particles are particles we're interested in. Some of the particles might be background, for example, the cell that we don't like. And we would like to have an image with the excitation off and the excitation on, very similar to what you would do here. And then we would like to, in kind of an image difference, if you like, directly extract kind of a 3D localization map of all of these particles. Yeah? So in this talk, I try to kind of give you like an introduction to what we have been trying to do to achieving this kind of three-dimensional goal. And I mean, of course, you can always ask, why would you like to do this? And I'm not going to go into a lot of motivation. For me, it's very simple motivation is kind of to say, look, everything around us is three-dimensional. Yeah. And just for this kind of 2D cartoon of the cell, we have several viruses here that are all tagged with gold nanoparticles. And it's kind of difficult to choose before you do the experiment which of these particles is relevant. You know, maybe what we would like to learn is happening here is this virus, or we decided to look here or here. So that's kind of a problem. Ideally, we would like to watch everything, and afterwards we can decide, okay, this was a relevant thing. Here's maybe an artifact, and yeah, here nothing happened. Huh? And kind of as a kind of historical motivation for me are these kind of seminal works on two-dimensional single particle tracking by photothermal microscopy, and also this optical coherence microscopy work from the laser group. Basically, these two things combined. So you can do really high quality 2D tracking experiment with photothermal microscopy, and you can actually do 3D microscopy by using optical coherence tomography. Yeah? And our goal, and my goal on this talk, is to kind of fuse these two things. Can we do 3D tracking of individual particles in kind of a 3-dimensional cellular world, if you like? Yeah? And that brings me to kind of a quick how-to guide to this talk. There are a lot of different concepts, funny tricks, and I'll try to keep you all on board. So I'll start off with a brief recap on what we've been doing in kind of holography and 3D localization work from single-shot images. I then move into something which we call all-optical lock-in imaging. This is kind of how can we implement a lock-in amplifier using a camera. And then ultimately, this is, I think everything is unpublished. We will then combine these two things and start doing photothermal or phototransient imaging in large 3D volumes. So you can see this is a real 3D volume here. We have 110 by 110 by 110 micrometers. So this is kind of the goal of this talk, and I hope we get there. Just to start off, I'd like to introduce this topic a little bit. I think we've all heard of holography, but if you have to explain what holography is, actually not that trivial. Yeah? You can look at Wikipedia and you see it is not trivial. So holography is the science of practice of making holograms. I'm not really sure what that means. But if you just look a bit back of what we know, we have a lot of inline holography that we are kind of used to. There's Gabo holography, and then here, if you're in the field of photothermal microscopy, I'm sure you've seen some of these acronyms, probably iSCAT or COBRI or IRIS or IRM, which are all kind of inline holographies. And then there's off-axis holography. I'll show you in a minute that this is very similar. In my talk, I'm basically exclusively using this off-axis holography. And before I explain you how it works and what it does, I'll just show you what it can do for you. Yeah? Just as a very simple example. So imagine here you have a 2-dimensional sample, and you have put a bunch of particles on your sample, and you're just moving them around. Let's say with a 3D piezo, for example. So you're just moving them. You're moving them left, right, up, and down, and you can kind of see if you move out of focus, the point split function becomes big, and so on and so forth. This is kind of a normal image that you could see on your microscope. If you do holography, you can at the same time, while you're doing this, you can recover the phase of this light. So you can see if you move out of focus, you get large spherical waves. It's like a defocused particle. And then ultimately, you can kind of combine these two things, and you can do some computational tricks, and you can recover the kind of 3D trajectories that we were applying with our piezo. In this case, we're just writing holography to show that it works. Yeah? So basically, you can use this concept to do 3D particle localization, even though you're completely out of focus. Yeah? So you might wonder, how does this actually work? And here's a very simple example. So imagine you start off with a plane wave here, and you illuminate the sample. In this case, it's just like a slab of a material A and a slab of a material B, and they have a certain shape, and they have different refractive indices. So once this plane wave propagates through this material, you see it requires some kind of a phase change here due to this object. So now the wavefront looks differently. And then in a normal experiment, you just put like a camera here, for example, and you detect the amplitude square of this electric field. So you would not see the phase at all. You just see, okay, we have a plane wave. What off-axis holography does, it just takes another normally called a reference wave, and it interferes the signal wave with the reference wave on a detector, and what you now get is kind of, well, an interference pattern interference term. So now you will detect, again, the signal square here, you will detect the reference square of this wave, and you get an interference term. And that's a typical, like, the signal electric field times the reference electric field. And here's kind of a cosine function where we have the phase of this object here. And the phase term, and this is important, this is like a phase as a function of y, as a function of this detector dimension, if you like. And that's because we have an angle here. So if you think about this, what it does to you as a function of y, this interference term will oscillate. And ultimately, you can use this to isolate the phase and the amplitude, and basically isolate this interference term from the other two. And everything else we're doing is kind of based on that. So normally, I directly jump into showing you how the experiment works and how you do this really with data. But I thought, given this community, I think iSCAT and inline holography are used a lot. So I thought I'd just put like two kind of brief slides to kind of put it back to back with iSCAT and typical inline holography, so we are all kind of on the same page, yeah? So very simple question, what about iSCAT and all the other holographies? And here just some kind of cartoon representations. This is what I just showed you, this kind of off-axis holography with the signal and the reference at an angle. And this would be kind of iSCAT or inline holographies, where you have the signal propagating in one direction and the reference wave propagates in the same direction. I'm sure you've seen this equation. And then we have also kind of self-interference holographies. I'm not going to talk about it, but for example, I think 2 weeks ago, Guillaume Bafoul talked a lot about this quadrilateral wave lateral shearing interferometry. It would be something like this. So if you compare it to this, it's really a minor change. So what's the result of that? And I'll just show you a bunch of inline holographies to maybe give you an example. There's a kind of classical inline holography where you do is you just have a plane wave, you illuminate a particle and you get scattering of the particle and you interfere the two in a detector. It has a lot of advantages. You can do like twin image illumination. This is important for Z propagation. You can obtain phase information. But on the downside is you kind of need to process this hologram here to actually acquire an image that makes sense from our intuition. Great is it works with a lenses. And there's kind of Gabor holography, you can already see. It looks kind of the same. The only difference is it has a spherical wave as an illumination source rather than a plane wave. And then we have here all these other holographies like iSCAT, for example. And all actually that changed with respect to, let's say, common inline holographies that you have moved your detector to where the particle is. I mean, of course, you're using an imaging system, but ultimately you place the detector in the image plane. And then what it does to you is you don't really have to do any post-processing of your image, right? You see an image and it makes intuitive sense. And there are also a lot of drawbacks with this. You have a problem, you can't really eliminate what is called a twin image. It is really difficult to obtain phase information from this kind of measurement. And we notice here the scattering square term and these reference, this interference term, they overlap, there might be problems, but it has also really, really like powerful advantages. It works really well with incoherent light and you can really easily normalize your signal to the kind of reference field, which is great if you want to do like quantitative sizing of particles. Yeah? So me personally, I like all of them, but I like off-axis holography, especially, sorry. And that's because it kind of combines all the positives of all of these holographies and it doesn't really have any drawbacks apart from that you need to do a bit of post-processing. But I'll show you in the next few slides that is, I hope, not too complicated. Yeah? So let's get started with the experiments. So this is just about implementing off-axis holography. And it's really, really simple. So you can think about it here. This is a cartoon again. You can see there's like a microscope objective here. Light comes out of the microscope objective, and here's your typical tube lens, and then you have like your CMOS camera or CCD camera if you like. And you can put any sample you like on top of the microscope, and then you can illuminate the sample either in kind of transmission from the top, or you could come in a reflection geometry. You could also place a dark field mask here. It doesn't really matter. In the end, you like obtain your image information on the camera, and then all you do is you send a reference wave here from the side on it. That's what I showed you before, if you remember the past few slides, yeah? And maybe you think, oh, this is really complicated, but it's actually not complicated at all. You can simply go on Thor Labs, you can buy a 99:1 fiber beam splitter, couple a coherent laser into that fiber, and then you use the 99 to illuminate, and a 1% you send on your camera, and you're done with the experiment. Yeah? It's not that complicated. And then in any case, so what you get from this image, I'll just show you some examples here. So what we did is we placed gold nanoparticles on this microscope. We put a dark field mask here to reject kind of the illumination beam, and then we illuminated this from the top. And then what we get is like a kind of, which looks like a dark field image, I would say, right? There's like almost no background. There's some black spots here, the gold nanoparticles. Really difficult to see. There's also this reference wave is on top of it. What you can do now is you can just take this image, you Fourier transform it, and what you obtain is kind of a picture that looks like this. In the middle here, what you have is the unmodulated term. It would be your E signal square and your E reference square. And then shifted are these interference terms, which are shifted because we have this kind of detector position dependent modulation. And all you do is you say, okay, I'd like the interference term. So you take a circle, you eliminate this guy, so you select this guy, you move it in the center of your image, and then you back Fourier transform, and you take out of your complex number the phase and the amplitude, and you're done. So basically, you isolate this, and you get the phase for free, which I think is fantastic. And And I'm not going to show you much about like the small details of the experiments, because I'd like to talk a bit about photothermal microscopy, but I just wanted to say it works really well. So you can do large scale imaging. What you see here is we did like kind of large field of view imaging of 20 nanometer gold particles with an NA of 0.7. So you can see these are almost like 200 micrometer field of view, relatively nice signal to noise ratio. You can use this to size nanoparticles. We didn't try to break any world records here, so we are able to image anything between 20 and 250 nanometer diameter gold nanoparticles, with I think a very, very precise size estimate. Here these widths are comparable to the specifications of the manufacturer. You can use this more in kind of biomedical applications to size, for example, extracellular vesicles. And you can also do more like kind of nanophotonics related works. So what we did here is we use different size gold nanorods that show like a plasmon resonance that shifts with kind of the length of the particles, which you see here is the amplitude, and you can then measure these amplitudes via off-axis holography. And at the same time, you can measure the phase of this scattering from these nanorods. So you can see as you move, for example, here through the resonance of this particle, you get like a pi phase shift as you move through the resonance. Of course, I was going to talk about 3D, so we need to kind of get to the point of 3D. So basically coming back to the video I showed you in the beginning, and you kind of, because you get the phase, as long as you have a sparse sample, you can get Z-localisation for free. So here's an example of this. So all we did is we made kind of a block of agar gel, and we doped this agar gel with 80 nanometer gold nanoparticles. And then all we do is we sit at one Z position, let's say here, and we record a hologram, and then computationally we can propagate this hologram up and down in Z, and you can see we can resolve a lot of particles, as long as the sample is sparse. Yeah? So we take one image, and then we generate this kind of 3D stack of images, and then we're able to localize particles. And then what we kind of try to do is we wanted to know, okay, how well does this actually work? So we took this agar gel block, we put it on our microscope, in this case an NA 1.2 microscope, 18 nanometer gold particles, and then we just stepped the sample up and down in Z with a piezo by roughly 60 micrometers in Z. So it's the Z position, absolute Z position with respect to the kind of focal plane of the microscope. And we just applied small steps, and you can see if you zoom in, let's say we look at the particle here that is initially 40 micrometer out of focus. We compare it to a particle that is almost in focus, and we look at these steps here, and you can see these are 100 nanometers, so we can resolve kind of 20, 15 nanometer steps, even though we are nominally 40 micrometer out of focus with this particular particle. And they kind of look identical. Huh? And you can quantify this, and you can say, okay, it doesn't really matter if I'm in focus or 15 micrometer above the focal plane or 15 micrometer below the focal plane. In this particular case, my deviation from the actual stepping I'm doing is on the order of 10 nanometer, maybe. Huh? So it works, it can work really, really well. And the only reason why we didn't take smaller particles in this particular case is that the agar gel itself scatters to an extent where we needed 80 nanometer gold to be able to discriminate them from the background. Yeah? Just to reiterate, all we do here is we measure one image at each piezo step position, and then we localize all of the particles over our large volume of view. Just as a last comment in terms of, is this actually interferometrically stable? I think that's is a valid question, and my answer is interferometric stability is not an issue, even though you have separated your reference wave from the kind of signal wave. There's no problems, and to verify this, what we did is we kind of separated the reference and the illumination. We then propagated independently over our table over 3 meters, which I think is a relatively unrealistic path length. And then we just measured the interference fringe on the camera. Here over 5 seconds, you can by eye, I think, not see very much change. And we can then quantify this. So we recorded these fringes over like 30 minutes and asked ourselves, okay, how much phase shift do we actually acquire as a function of lag time? So for example, in this particular case, so okay, if I wait 1 second, my mean lag phase shift is roughly 0.1 radians. Yeah? So that means you have to acquire something like 3 seconds to lose 1% of the signal. And on a 100 millisecond timescale, which is still very slow for typical CMOS integration times, you lose something like less than 0.1% of your signal. So if you think in terms of signal to noise ratio, if you want to resolve the phase problem here, you need to acquire 1 million electrons per particle, let's say, is not really realistic. Yeah? And most importantly, we are doing off-axis holography. We are measuring the phase, so nobody forces you to measure 100 seconds and then average everything and lose your signal. You can just correct the phase drift and then average. So there is no problem at all. Okay, so I hope this is kind of relatively brief mentioning of what we're doing. I could convince you that holography or off-axis holography can be really useful to do like sizing of small particles and especially 3D localization. And I'm going to move towards the kind of all-optical lock-in part. So this is kind of trying to use these concepts and move towards something that allows us to do photothermal imaging by using a camera. And, sorry. The reason for this work is kind of directly related to the way we normally do photothermal imaging, which is like we have a pump and a probe. We illuminate our sample in a kind of near confocal or confocal fashion, and then we raster scan our illumination and probe beam over the sample. And that is fantastic because we can use photodiodes and lock-in amplifiers. We can get impressive signal-to-noise ratios. However, and you can see this really nice in this work here, you get a really massive problem if your particles move while you're acquiring. So in this case here, you see a static particle, a very nice point spread function, amazing signal-to-noise ratio, and here's kind of a similar or maybe the same particle, but what happened here is the particle moved while they were raster scanning the image. And you can already see this does not really look nice anymore. Yeah? So my point saying is great, it has a problem with dynamic samples. And then if we look into biophysics or biology, we kind of realize that cameras these days are what people like to use if possible. So very simple question is, why do we have to use a lock-in amplifier? I want to use a camera. And I think the answer is pretty clear. Normally, the lock-in amplifier allows us to high frequency modulate our signal so we can extract a small signal with a very, very high signal-to-noise ratio and the short noise limit, whereas cameras are really slow. So we would kind of be here to get a terrible signal-to-noise ratio. Yeah? So to summarize, I'd say we need this thing here because we need to do high frequency modulation. Slow cameras don't allow for this. Of course, there's also a short noise thing, but if you look into modern cameras, it's just a side note, you can get something like 10 to the 9 photons per second per pixel, which is, of course, not a photodiode, but if you do 10 by 10 pixel binning, you get into a 10 to the minus 5 sensitivity in a second, which I think is a very decent number. Huh? So here's our all-optical lock-in camera, and I'll walk you through it because it is relatively complicated to follow. So we'll start here. There are two boxes. One box is called the imaging box, and one box is called the interference box. I'll just start here. Huh? So what you have is you have a microscope objective. Up here you put your sample. The sample can be anything. Let's call it gold nanoparticles because it is easy. So you illuminate the sample with your probe here, this purple beam from the top. You have a dark field mask here to reject the probe beam, and then you would image the scattering onto a camera. So it's kind of a dark field microscope until this point. Now we want to do photothermal or phototransient imaging. So you take a pump pulse, you also send it onto the sample, and you illuminate the sample, and you modulate the pump. Sometimes the pump is on, sometimes the pump is off. And if you would now do a very non-lock-in camera-like experiment, what you would do is you would acquire one image with the pump on, and then you would acquire another image with the pump off, and the difference would give you the differential signal due to the pump. The problem being it's very slow, as I already mentioned. So to circumvent this problem, we put our off-axis interference setup down here, and it's now a little bit more complicated than the single beam interferometer that you saw before, but it's very similar. So all we have here is we have a time delay because we're using pulsed lasers, and we use 2D grating again because we have pulsed lasers. The most important part is here. Rather than using one interference or reference wave, we are using two. Yeah? And we both image them onto camera. And we have a chopper here. So what we do is the following. We have a laser. The laser emits laser pulses at a certain frequency. All the time we are probing the sample on our camera. And then, as I already mentioned, with the pump, every other laser shot, we illuminate the sample. And then all we do here is we modulate our reference beams. So we take one reference beam, call it the reference on beam that we use to interfere with the probe when the pump is on, and another reference beam here, we interfere with the probe when the pump is off. While all of this happening, we expose them with the camera. We don't care how fast these things are. The camera just integrates and integrates and integrates. And then as previously, we can use this off-axis trick that transfers our information to isolate the image. Yeah? Because what is happening here is we have these two waves and they come at different k vectors onto the camera. One comes from here, let's say from the top left into the center, and the other one from the bottom left into the center. So what this does, if you remember the introduction, is we have our signal wave, it hits the camera, the reference comes at an angle, here's the angle. You can see here the phases, there's a phase difference. The phase difference translates into a modulation of the signal, this oscillatory modulation. And now, because these two waves coming like off diagonal, our off wave will modulate the interference term in this dimension, and the on wave will modulate the interference term in the other dimension. On an image base, what happens is you have your raw image. Here again, these are gold nanoparticles. You can zoom in, you can kind of see this interference pattern already. Now you Fourier transform and you see it, rather than having one diagonal as before, we have two diagonals. Yeah? And one is the pump on image is here, the pump on term, and the pump off term is here. And then you select this one, you back Fourier transform, you select this one, you back Fourier transform. And from one image, one camera recording, you're able to directly obtain your pump on and your pump off images, and it's completely irrelevant how fast you modulate. The camera doesn't care. Huh? To show you that this works, I'll just show you a few pictures. So again, here, these are our nanoparticles, in this case, 100 nanometer particles. I just wanted to mention we're using an amplified femtosecond laser here, just to make sure that the time delays make sense. And all we do now is we pick a bunch of these particles here, I mark them with circles, and we scan the probe with respect to the pump pulse. And we record the signal of these particles. And you can see as we scan the probe of our pump, initially the pump off signal and the pump on signals are the same because we are imaging the particle before we photoexcite it. Then we photoexcite the particles here around time 0, and you can see it change. And then it decays. And importantly, the change is only happening in the pump on interference term, whereas the pump off does not see the probe. And because we're imaging, we don't have 3 or 4 particles, we have a massive field of view, and we see all of this at the same time. You can see the images at different wavelengths of the probe. Before time 0, we see nothing. And then as we move to time 0, we see the particles light up, depending on where we are with respect to the surface plasmon resonance of these particles. We see different signal magnitudes, and then we see the decay. And most importantly for me is at least, this is recorded in kind of a single shot per image fashion. So we're not raster scanning. And of course, you can, if you want to, you can use this for spectroscopy. So a very simple kind of model picture. Imagine you have your gold nanoparticle that is initially hot. You photoexcite it. It's initially cold, of course. You photoexcite it. It heats. So the scattering spectrum changes slightly. And then we can use, again, our wide field lock-in microscope to image this photoresponse as a function of probe wavelengths and pump probe delay. So here just, I think it's a roughly 80 gold nanoparticles, and you can nicely see the decay of the photo-induced heating or hot electron dynamics. And yeah, you can see the mean signal. You can see here kind of histogram distributions, and these are kind of representative of the single particle image. And all of this again is acquired in a wide field fashion. And of course, we started working on this, and then clearly one of the standard questions is, okay, how sensitive can we be, and are we specific? And I mean, we had a very, very low magnification or NA microscope objective here in this particular experiments, which is an NA of 0.1. So we were struggling a little bit, but we managed to image 100 nanometer, 80 nanometer, 40 and 20 nanometer as well. Whereas in the later case, you can see it's really difficult for us to detect them in scattering. Whereas in the phototransient imaging modality, we can nicely resolve the particles after photoexcitation. Yeah? And similarly, we were comparing gold nanoparticles. So these are many measurements. You can think about each line being one of these transient dynamics here. So we're comparing gold nanoparticles and like dielectric lattice spheres. And we're just asking ourselves, okay, are we actually specific? And the answer is yes. If you photoexcite the gold nanoparticles, we see heating. If you photoexcite the lattice particles, we don't see heating, meaning the differential scattering signal of the gold changes as we change the pump power, whereas the differential scattering signal of the lattice piece is 0, irrespective of the pump power. Okay, I know it's a relatively complex kind of experiment, but I hope I could at least give you an idea on how this all works. And now in the last kind of 5 minutes, I guess, I just wanted to show you how you can kind of combine the 3D aspects of the standard off-axis holography and this phototransient microscopy to go really towards 3D imaging of photoexcited particles. And just to recap, I just once more, I'll show you another picture. We can really 3D localize. So here's another example. So imagine these are particles. You can maybe see them by their Poinsot functions. Here, they're slightly defocused. We are roughly 2 micrometers out of focus. And we always, with our holography, we obtain the amplitude image, and simultaneously we obtain a phase image. And I think here the phase image really shows you nicely the defocus here as kind of spherical waves. Then what you do is you take this kind of information, you do some convolution operations, you can call it digital image propagation if you like, and then you can refocus an image like this. So I just put this box here. So if you computationally focus it, you get this, and if you manually move your sample, you get more or less the same. So very good agreement, yeah? So you can tell me, okay, look, I can already see where the particles are, right? I don't really need any tricks here, but this really works also for large defocus. And I think data is always the best way to convince someone. So we did the same experiment, now we defocused 1 micron, 10 micron, 14 micron in the other direction, 30 micron. This, for me, looks like a spectral pattern. Of course, we have the phase images that I'm not showing you. So we use this information, we refocus the images, and you can see, irrespective of where we actually were, and we recorded this, we get the same image back. Yeah? Here's like a zoom in. They look very much the same. And we can quantify it because it's a static sample. So all we did now is we took all the particles of each individual particle. Here, for example, this guy. We took the mean scattering amplitude and compare it to the scattering amplitude in the individual images after refocusing. And you can see that they basically nicely correlate. So it means it doesn't matter if you're 33 micron out of focus or almost in focus, we will get the same signal after numerically correcting for the focus. Yeah? And now all you have to do is take this information and combine it with transient excitation. And again, it's the same image, if you like. So we have an S-recorded image, we're out of focus here, and you can see before time 0, we see nothing. After time 0, we see kind of blue patches. These are the out of focus particles, and it kind of disappears. And now, once again, as before, we can computationally refocus this information. You see, again, nothing. Now we nicely see the particles light up, and we see the decay. So all of this is nicely compatible with the phototransient excitation. And as before, if you remember, the amplitudes of the refocused and the mean amplitudes nicely correlate. The same is true for the differential scattering signal. So irrespective of where we are, we see the same thing. So let's go to, how much do I have left? 2-3 minutes, Sebastian?
Yeah, 2 to 3 minutes.
Wonderful.
Is fine.
Okay, perfect. So I have enough time to wrap up. So I think this is all nice, but these are static samples so far. So it's not really what we want. So now in the last few slides, I'm going to show you that this also works for non-static samples. So you might recall this agar block that we had here as a kind of a static 3D sample. We were able to record a single hologram, then propagate the hologram around, localize the particles, and then kind of get all the positions. So of course, the same should work for dynamically moving particles, right? We can take a single snapshot of our particles, then we can generate a stack of propagated holograms. We can localize all the particles, and we take another image and we repeat and repeat and repeat. And it's exactly the same as doing 2D tracking, just in 3D tracking. And I'm not going to go through the details, but basically this is what we did here. So we just took 100 nanometer gold nanoparticles, we dispersed them in water, and we were just watching them diffuse in 3D by recording holograms. And in this particular case here, I think these are roughly 80 nanoparticles that are freely diffusing in 3D. And this was acquired using a 10 millisecond integration time. So nominally 100 frames per second, but we recorded at half a frame per second. And you'll see the next slide why we didn't go for 100 frames per second. Yeah? So the reason is very simple, because when you look at this, and I'm telling you, now we're going to do photothermal, phototransient imaging with excited particles, like if I see a signal or not, it might be difficult to convince you that what we see is real. So we thought, okay, let's do it. Kind of a trick, right? We can follow each individual particle as it diffuses. So what we wanted to do is we say, okay, we'll record a camera frame before time 0. We should not have any phototransient signal. Then we're going to move the time delay to a point where we should have signal due to the photoexcitation. We record another image, and then we just go back and forth and back and forth and back and forth. So in our holography picture, what should happen is The pump off channel should always kind of have noise, but the same signal. Whereas in the pump on channel, if we are after time zero, we should have signal. If you're before time zero, we should not have signal. So it kind of allows us to validate with a kind of very simple change that what we see is really phototransient changes and not some artifact. Yeah. And this is why we record it at 0.5 frames per second, because it takes time to move these translations. And it actually works. So here's again, this is what we do. And we can just take histograms of all our differential scattering signals of the particles recorded before time zero. You see they're nicely centered around zero signal. And then if we go to positive time delays, you see the distribution shift. So we're actually generating photo-induced signal. Huh? And then you can look at this in a single particle base. These are like computationally refocused images, and you can see in the difference every other frame we see the signal. Whereas if we take off resonant particles, we never see the signal. And here's just an example to wrap it up. So imagine we record this kind of hologram here. Now we take this area, we propagate it by 10 micrometer. Here's a particle, and we have many, many frames. The particle moves up and down. We follow it by propagation. If you're before time zero, there is no signal. If you're after time zero, there is no signal. And I think there's a video. Maybe this will even play. Yeah, here it is. So this is the raw here that you see here. And here's the propagated where we follow the particle. Here's the transient signal. And let's hope it repeats in a second. Let's do this once more, if I can. Yeah, so you see before time zero, there's no signal, and then as we cross the time zero mark, the signal appears, and the particle is diffusing through here. So ultimately, what it allows us to do is we can follow this particle, we can record its 3D trajectory, and at the same time, we can change the pump probe time delay here, and we can record the transient signal change of these particles at nominally 100 frames per second. Okay, with this, I'll very briefly summarize. I hope I could convince you that off-axis holography or holography in general is really great and it's useful for kind of 3D localization imaging. I tried to convince you that you can do lock-in-like signal demodulation on a camera, and we can combine these things to go towards 3D localization microscopy over large volumes of view. And I'm not going to give you a big upload. This is going to be continued. I hope we're going to reach the cell stage soon. And with this, I'd just briefly like to thank Giulio and Franco from Milano. They were involved in these experiments, which were performed in Milan. And of course, my group is Nick, Unai, and Lisa that were all actively participating in these experiments. And all of you for your attention. Thank you very much.
Okay, thank you, Matz, for the wonderful talk with very impressive images. And so now it's time for the questions. So please write in the chat, or you can ask directly. Okay, Michelle want to ask. So Michelle, go ahead.
Yeah, thanks, Matt. Very nice, impressive results. I wonder, a question which often arises in super resolution and maybe also here. Of course, you can image through 13 micrometer of a medium. How sensitive is your imaging, phase and everything to the index fluctuations of this medium? If you would like to image through a cell, for example, how serious are the index fluctuations through the cell? So the one possible problem is scattering, but of course also the phase differences that may scramble your phase reconstruction may be an issue. So have you looked into that?
No, obviously we haven't looked into this because we're just starting. I guess the problems will be very similar to kind of fluorescence microscopy experiments, unless we start correcting. I mean, you can do some phase corrections in holography. I expect similar kind of issues. So of course, if you want to precisely localize within a nanometer where exactly you are in a cell, there might be problems. However, I mean, I think we're more trying to go towards dynamic scenarios. And in that case, at least for me, the main question is very often like relative change.
But the phase front reconstruction, is that critical? I have no idea of the orders of magnitude.
I mean, it's a bit, so you imagine if you put a single particle and it scatters, and then your scattered wave propagates through the funny medium. Yeah, of course, you're going to get problems somewhere in the phase front, but because you essentially integrate the entire spherical wave, I expect the problem to be small because you're kind of sampling a massive cone of your cell. It's not like, of course, if you're in the near field, there might be problems, but in terms of the projected light, I don't see big issues. Of
Okay.
course, if
So,
you talk in tissue, I think,
yeah.
then you'll have the same.
So in principle, your answer is I have all the phase information. So in principle, I can also go back to this. I can reconstruct also this index profile.
Yeah, I mean, of course, it's a sensitivity question, but you know it's a spherical wave. You should be able to see more. How easy that is not clear, but it is similar to kind of a guided star problem in wavefront correlation.
Yeah, exactly. Yes. Okay. Thank you very much.
So, okay, question from Xiaolong Say, please ask.
Hi, Matt. Great work.
Okay.
I have a following question to Michelle's. So regarding the sensitivity and the phase, in one of your slide where you show the digital focusing, there's a very minor difference between the digital focused image and the manual focused image, I think. Very little, but so my question is, fundamentally, so the difference I saw was there seems to be some speckles in the computational focused image compared to the manual focused image. So I know there is a resolution reduction by a factor of 2 or a little bit more than 2 due to these off-axis holography. So my question is, now you try to use a 2D sensor trying to capture the 3D wavefront information. So is these speckle or these kind of fringes due to the, is it a technical issue or a fundamental issue of holography?
I mean, okay, the images okay, it's a simple question that has a massive answer. So in this particular image, you can still see the screen, right?
Right. Yes.
Yeah. Okay. So I think you're talking about this particular image here. So we acquired these images with a femtosecond laser in Milan. So it's kind of like a very incoherent light source, if you like. So some of the speckle we are generating, or we would be generating with, let's say, a coherent light source like a CW laser, is kind of masked in this particular manually focused image. So my answer is, if you would repeat this experiment with a coherent, like a CW laser, both images would look identical in this particular case. It has nothing to do with the resolution reduction, and that is mainly due to the fact that also the image on the bottom here is an off-axis image. So I always record off-axis. This is also off-axis recorded, but it is recorded with the sample being in focus. The lack of speckle is due to the fact that we're using an incoherent or relatively short coherence light source.
I see. So these, so those are not fundamental issues.
No,
those are just technical issues that can be tackled.
Yes.
Okay. Thank you.
I mean, there are, of course, if you're very far out of focus, the problems start appearing, of course. So if you imagine you have many particles in one focal plane, many particles in another focal plane. Now, as you propagate, you get funny interference effects that generate speckle that is not there. That's why, I mean, I'm talking about 3D localization. This is not a 3D technique that allows you to measure a very dense sample. For this, you would need something like tomography, for example. So the more particles you put into your sample, the more difficult it becomes to get the perfect image. That's something to keep in mind. So for a very dense sample, there would be a massive speckle problem, and then at some point you can't do anything anymore.
Got it. Thank you.
Okay, Randall has a question, please.
Hi, Matz. This is a beautiful series of stories. Thank you.
Thank you.
Can you go to slide 15? I have a kind of a minor detail I want to ask for some more clarification. Okay.
Yeah?
Yes. Yeah. So on the left, you said, oh, okay, it's very simple. You just need this 99:1 beam splitter. Can you talk a bit more about how you've laid out the optics to sort of steal away the reference beam and then combine it at the CMOS detector?
I mean, there are many. I mean, we have many implementations of the same story. Yeah, so we use often almost incoherent light in terms of femtosecond lasers and so on and so forth. Things are more complicated there because you need to worry about phase fronts and all of that. In the simple scenario that I kind of mentioned here is we use a diode pumped solid state laser, so with a relatively long coherence length. So we don't have to worry very much about the actual physical delay. So we don't have to be exactly at the same delay from the reference to the illumination beam to get interference. So that eliminates that. The current setup that relies on this particular set of optics is literally, you have a fiber coming from the top with a lens that collimates the fiber, and then another lens which kind of focuses onto the sample, and a dark field mask here. And then you have the other part of the fiber, which has a collimation lens that is with a long focal length. You get a massive beam, and we simply send it on the camera at the correct angle to get separation here between these two terms.
So that reference beam is basically traveling through a different length of fiber, doesn't go through the objective, and then you use some other free space optics to then come in at an angle at the objective.
Exactly, yes, exactly. And of course, if your light source is like a cheap laser diode, then you might have a problem. But if you have it is €100 coherent laser, I mean, 532.
A bargain,
and
yeah.
Yeah, and there's no problem. So it really depends on your light source. You can make this very complicated for yourself or very easy. Yeah, but
and I guess with this very long coherence length laser, you also you're sensitive. You're not so sensitive that you have to worry about just fluctuations of the fiber itself. Minor bending changes that could alter the phase. All that gets absorbed because you have this very, very long coherence length laser.
I mean, these things you would see, right? Because the coherence length has nothing to do with like mechanical instabilities. But I mean, the fiber, there's no reason why the fiber should move. I say it like this. I mean, we characterized stability on this particular setup, and we have not really seen any issues. Of course, I mean, if you start treating your setup not nicely, you might get into trouble. But it is in general very, very robust as far as.
I mean, if you try to make just a fiber interferometer in a room that is fairly temperature stabilized, you'll still see sort of interference fringes wandering. And I think it's interesting that you don't see that.
I mean, we see that. Don't get me wrong. It's just it is not important, because we acquire our images. It takes, let's say, 50 milliseconds, 10 milliseconds to acquire an image. If you like a second, then we have this hologram and we extract the interference term. And now if you wanted to average many holograms, we can always make sure they're in phase. It's all computational, So it's like if you have a cosine function, you can on your computer add a phase offset to it to make sure it interferes constructively with the sine function. There are changes and slow drifts, but all of this is not a problem if you want to average, because you can just add the number. It's a complex number, you could just add anything you want to it.
Makes sense. Thank you.
Okay, I think this will be last question. So question from Mar. Please go ahead.
Yeah, hi. Thank you for the talk. I had a question because you were talking about the coherence length of your laser, of your light source, but have you looked into the spatial coherence of it? Because I can assume that since you want to do volumetric imaging, that could also play a role.
Yeah, I mean, okay. Like the simple answer is we have not looked into the spatial coherence of the light source, because it's like it comes out of a single mode fiber, so it should be in a single spatial mode. We have performed similar experiments with LEDs and so on and so forth, and that I mean, you can, as far as I'm concerned, I wouldn't know how to do a 3D holography based on an incoherent illumination based on a single picture, because the scattering you get from a single point in 3D will not interfere with anything at a different plane, or with very little at least. So you need a spatially coherent light source if you want to do this large volumetric localization holography. Otherwise, the particle scattering from a specific point will simply not interfere on your detector.
I guess what I'm thinking is more of a raster scan type of scheme, because in principle, what you would have is a speckle background. Like it would be either in like two axes, right? You would have it in longitudinal mode, and you would have it in the spatial mode. And I would imagine that if you were to do a raster scan type of scheme measurement, then you would have something which is very spatially and in both directions, it would be incoherent.
No, I mean, you can. I mean, you can do such things, but I would say it is most likely not going to work. And the reason being, even if your reference wave is kind of spatially coherent and temporally coherent and can interfere with the scattering that you generate, let's say, at one particular point in your sample. Now you scan, your raster scans through your sample, you get to another point, let's say hit another particle again, you get scattering. All of this propagation business relies on the fact that what you measure is a realistic electric field. So the realistic electric field means the scattering from particle A has to interfere with the scattering of particle B. But if you raster scan and you illuminate first particle A, then you illuminate particle B, there's no more interference between the two. So you merge them essentially into one object, and when you propagate, you get funny stuff. You need to make sure that your sample has a correct interference pattern to be able to computationally reconstruct it from the hologram.